Today we're going to talk about anti-reverse engineering. Stick to the end if you want to learn how hackers make their malware undetectable and difficult to analyze by reverse engineers. Right, so first let's start with anti-debugging. So in anti-debugging, the malware prevents analysts from debugging the code by suspending the process of the debugger. So as you know, debuggers are used to analyze the malware code or maybe the software code to detect issues, bugs, vulnerabilities. The thing is, debuggers are used to analyze malware as well. So when a malware implements the anti-debugging technique, it seeks to prevent analysts from analyzing the code of the malware to hide its behavior. So how it specifically does that? It does that through API calls. For example, Inium windows and suspended thread are API calls that can be used by the malware to look for processes that indicate the presence of debugger. Once located, the malware would suspend the debugger process, as we will see later in the practical scenario of this video. Now, how to prevent this from happening? What you have to do, you have to locate these API calls in the malware code and fill them with nope. Nope is no operation. And of course, if you are watching this video, you must know what is nope, so no need to explain this. All right, moving on to anti-VM. It's another tactic used by malware authors or malware developers to detect the presence of VM software. So why it does that? Because when a VM software is running, it indicates that an analyst is trying or maybe trying to analyze the malware. So how the malware detects that the VM is running? First, it uses the Inium Process API. Through Inium Process Windows API, it lists the running processes and looks for any indication that a VM is running. As you know, VMs use processes, and for example, VMware, VirtualBox, these processes can be located easily by a malware. So once located, the malware may stop the process altogether or may not run at all to prevent the analyst from analyzing it. The next technique the malware uses to detect that the VM is running is check for uninstalled programs. Malware has the ability to check for uninstalled programs. If it detects that VMware, VirtualBox, or any other virtualization software is installed on the OS, it will not run at all, or it will run only a specific part of its code. Check OUI. Now, OUI are identifiers that a virtualization software uses to generate a MAC address for the virtual machine, right? So basically, let me show you here. For example, as you can see, this is the documentation page of VMware. And here we see an OUI allocation. VMware organizationally unique identifier allocation assigns MAC addresses based on the default VMware OUI. So your VMware or your virtual machine has a MAC address assigned by the software that you use to run this virtual machine. For example, VMware uses this OUI to generate the MAC address. Here is the MAC address format. According to VMware OUI allocation scheme, a MAC address has the format where 005056 represents the VMware OUI. Okay, so now the malware has a unique identifier to look for when the malware wants to detect the presence of VM. So by locating these numbers or looking for these identifiers, the malware can actually find out if the machine is running a VM. Check resource consumption. Now, this tactic is used, but not that often, because the resource consumption may not indicate that a VMware is running. For example, a VM may be configured to run on 4 GB and 2 virtual CPUs, right? Okay. Now, your machine, this is for the VM. Your machine may be coming with maybe 16 GB. I mean, most computers do not run on less than 16 GB these days. And let's say it has i7. Okay. Now, the malware, when it detects that there's a resource consumption of 4 GB and 2 virtual CPUs, it may predict that a VM is running. But the consumption of 4 GB out of 16 GB is normal these days. So malware authors may not use this tactic alone to find out if there is a VM running on the system. Okay, so now how do we deal with this? So as an analyst, how do you deal with malwares that are able to detect VM existence? What you're going to do, you can use VMware clock or VBox clock. These are PowerShell scripts that can be used to hide the artifacts of a VM. For example, this is VBox clock, which is a PowerShell script that attempts to help malware analysts hide their VirtualBox Windows VMs from malware. This is for VirtualBox. Now for VMware, you have VMware clock. So VMware this is the same script but designed to run to hide VMware artifacts. Okay, the resources in this video, specifically the lab part, is part of TryHackMe Anti Reverse Engineering room. You can use the machine here or the deployed machine to be able to explore the anti-reverse engineering tactics. So first, let's talk about the anti-debugging. We have anti-debugging first. We have a debugger running here, and we have a malware. Basically, we have suspend thread and we have VM detection. Let's talk about suspend thread. So as an analyst, first you want to analyze this malware using the debugger. So you go ahead and open the debugger, and from here, what you want to do, you want to import the malware. So open suspend thread, and now the malware is imported. So if you want to run the malware, what you have to do in this debugger, press on F9 or press this button. This button. You run, and now as you can see, the malware is running. Go here and press F9 2 times, and as you can see, this is the output shown by the malware, and it looks like it's trying to suspend the debugger. The debugger found with PID 3920 suspending. Okay, so the malware now is suspending the debugger. If you try to interact with the debugger, as you can see, it is not responsive. Go to Task Manager and check out the process. So this is the process responsible for running the debugger. As you can see, the status indicates that the process is suspended, and that's because the malware did that. That's an example of a malware that suspends a debugger, or is able to detect the presence of a debugger and suspend it. Now, as an analyst, of course, you can go ahead and end this task. You can start over, but this will happen again. You will not be able to peacefully analyze the malware. So what you have to do, you can go ahead one more time, open the debugger, import the malware in question, and you will want to find out the routine responsible for suspending the debugger. You will want to find this and fill it with nopes. So after we imported the malware, we want to skip to the beginning or the entry point of this code. You can use F9, so press F9 once, okay? If you press F9 two times, it will run the sample. You want to press F9 one time. Of course, I'm talking about this debugger, right? Because there are other tools that can be used differently. So F9, and here I am at the entry point, and there is this call suspend thread, as you can see here. So I want to deal with this. I want to locate all the lines, all the routines that call the suspend thread API. So what we have to do, right click and search for the current module, click on intermodular calls. So here at the very bottom, you can search for the module. For example, I'm looking for suspend thread. Okay, let's try with uppercase. Yeah, sometimes you have to consider the case sensitivity. So here, this is the call, and I'm gonna double click on this. It will take me right to the routine itself. So it starts here at this memory address and ends here. It's actually located by this arrow. So this is the full routine of the suspend thread used by the malware. So what you're gonna do, you're gonna right click here on the suspended thread, locate the binary and fill with nopes. Click on OK, and this will fill the suspended thread function with nopes. Now when the code runs, and when it reaches the stage of suspending the thread of the debugger process, it will execute the nopes that we have filled in. Okay, we're not finished yet. What you have to do, you have to go to the patch view, patch file. Now patch file allows you to export the settings that you have applied, because when you close the debugger and run the sample again, it will run the suspend thread again because the settings are not saved. What you have to do, you have to patch them. So export these. Your patches overlap with relocation regions. This can cause your code to become corrupted. Click on continue. And we're going to export them to desktop. We're going to call them suspend. And okay, so now after we have implemented the settings, we have filled the suspended thread with nopes, we will want to continue the execution. So here, click on run. As you can see now, the malware is running. Now the malware claims that it detected the debugger again, PID 4252. Now it's supposed to suspend the debugger. Let's see if this happened. As you can see, I can still interact with the debugger. I can still click things on the menu, which means the debugger is not suspended. Okay, now let's close this. Okay, now let's open this one more time. Now what you want to do, you want to import the sample, and then you want to go to patch file, import, click on the patches that you have imported, exported in a while ago. Okay, now these have, and click on patch file. Failed to save patch file. All right, so we're going to okay, and then run. Double click or click F9 twice. Let's run from here. Again, run. Let's see. And look, I'm still able to interact with the debugger. That's because I have imported the patches, right? Let's look for these patches. So from here, we can go to search for intermodular calls and locate the suspend. Again, as you can see, there is no suspend because it has been filled with nopes. Before the entry point here, if we take a look at the instructions executed before, I'm gonna scroll at the very first. Okay, we have these two lines: proceeding with non-malicious activities or proceeding with malicious activities. And these two operation modes, as we said earlier, it depends on the outcome of the temperature readings. So scrolling up, let's see here, what do we have? So we have this line, terminal zone temperature. Looks like here is where the temperature is being read, and is indicated by this memory address here. So what we want to do, we want to skip the routine when it reads the temperature, because if our machine is virtualized, we want to fool the debugger or fool the malware from reading the value of the temperature, because if it's able to read, it's going to proceed with non-malicious activities, or it's going to hide its intentions. We're gonna have to modify the instruction pointer. The instruction pointer here will refer to the instruction or the memory address of executing the VM detection routine, right? And when the VM detection routine is run, it's going to read the temperature. To prevent this from happening, we want our program to start from here, at this memory address. Okay, we don't want the previous parts to run, because it's going to read the temperature. So we want it to start from here. So we're going to have this memory address copied over the instruction pointer to execute it. Right click, modify value, and here we can write the memory address. 004 01134. Okay, let's see. As you can see now, the instruction pointer points to this address. Right, so what I'm expecting here, I'm expecting the program to proceed with malicious activities, which means that the malware was not able, or the malware now sees that it is interacting with a physical machine, not a virtualized machine. So it's going to proceed with malicious activities. The third method malware developers use to hide the intention or the behavior of the malware is packers. Now packers most of you know what are packers. Packers basically compress, encrypt, and encode the code. So what packers specifically encrypt or encode? Packers look for variable names, function names, code syntax, and indicators of compromise. By encoding these key pieces of information, or by encrypting these key pieces of information, it's going to be difficult for static analysis to proceed smoothly. So if you are intending to analyze the malware statically and it happens that the malware is backed, it's going to be a lot more difficult to do that. So that's why we always recommend to dynamically analyze the malware when we find out that it is backed. How do you know that the malware is backed? We use tools such as Detect It Easy and PE Studio. As you will see in the practical scenario, these tools can identify the type of packers. Still, these tools may fail in identifying the packers used, right? So therefore, dynamically analyzing the malware by opening it and interacting with it is the ultimate way of revealing its behavior. For example, encoding can be base64. Encryption can be AES. Okay, these kinds of packing operations can be applied on the code to hide its behavior. Okay, now what are some of the packers used? We have PE log, we have Temida. These tools can be used to pack the malware or the code. Now let's have a look at some of the samples that are packed. So we have here packed these two samples. By the way, again, you can have access to these samples by subscribing to TryHackMe. As you can see, this room is only for subscribers. So maybe you have to subscribe to their monthly plan to be able to access the resources in this room. So I'm using the resources in this room. All right, so go back to packed. So we mentioned that we can to detect that a packer is used by using Detect It Easy and PE Studio. So you can search for Detect It Easy from here, or you can use its right-click functionality, because when you install Detect It Easy, it's added to the context menu. Right-click on the sample and click on Detect It Easy. Okay, do that, and as you can see, Detect It Easy will tell you if the sample is packed. We can look here at the packer used, and it indicates that the packer used is UPX. Another way to find out if the malware is packed without looking at this, you can click on entropy. Entropy indicates the level of randomness or uncertainty in the sample. The higher the entropy, percentage-wise, the more likely the malware or the sample is packed. Click on entropy, and as you can see, the entropy is 97%, which is too high for a sample. Even if it was a legitimate sample, such as a software with a license to be protected, it wouldn't have such high percentage of randomness. So 97%, there is a packer used to pack this sample. And here we can see the sections that are packed. So the header, portable executable header, is not packed. Other sections, such as section 1, is packed. Okay, we can have a look at the sections packed by using PE Studio. So we can open PE Studio from here and import the sample. Packed. Okay, now the sample is being imported. Okay, if you look at the sections, you can see that there are unrecognizable strings such as UPX0, UPX1, UPX2. These are the values for the sections. We know that a portable executable file has recognizable sections such as rdata, rtext. These cannot be found here. Instead, we have these values, which means that a packer is being used. Okay, now we know how to detect that whether a file is packed, how to unpack the file. Now to unpack the file, we have unpackers such as Temida, and there is an online resource as well that can be used to unpack a file. So it's called Unpack Me. So if you go to Unpack Me, we can find the resource here. We can have to sign up and upload the sample, and it has a paid version as well. I'm not subscribed to this service, but you may consider using it if you want to analyze the samples. Okay, back to the lab. All right, Now that we know how to find out if a sample is packed, and we know some methods to unpack the sample, but these methods are not always reliable and don't always work. What is the definitive way of unpacking the sample? So now we know that this sample is packed. The malware named packed, it is packed, right? Okay, good. How to extract the unpacked version of this sample in order to analyze it? To extract the unpacked version, we're gonna have to open the malware and interact with it. You can go to the debugger of your choice. We're gonna stick to the one with this room. Click on File, Open, locate the sample, and now we have the sample. We can press on F9 to have a look at the entry point. This is the entry point of the sample. Okay, now again, a packed sample is first packed, and when it is run, it is unpacked. That's why we're gonna have to run this sample. This is the entry point of the sample. Remember that when dealing with a packed sample, we want to extract, our aim is to extract the unpacked version of this sample. So we're gonna have to locate the end of the routine here. The end of the routine highlights the point where the sample has been successfully unpacked and saved into memory. How to find this point? Well, it's tricky. We're gonna have to search through the code. So the entry point starts here. We're gonna have to scroll down because this point comes after the sample has been unpacked and saved into memory. So we're looking for, so take a look at this. We have repeated patterns, right, of bytes being added to the registers. And we have this instruction, jump, packed, and there is a memory address. Now we can step through and follow this memory address. Before we do that, let's set a breakpoint here. So we can right click and set a breakpoint. So now I have a breakpoint at this location. If you continue running by clicking on this, okay, one more time, and now we are brought right to the location where we have set a breakpoint. Now this is the location after which, as you can see, we have repeated patterns, right? This would indicate that this is the instruction that when the code reaches, indicates that the code has been successfully unpacked. How do we verify this theory? We're gonna have to jump to this location here, indicated by the instruction. So we can right click and step through to this instruction, or we can just click on debug and select step into, not step over, step into. By selecting step into, we're gonna jump to this location, and it takes us to this address. This is where the malware starts to unpack. Call packed. Here the malware starts to unpack and saves itself into memory. So having done this, we can now go to plugins, Scylla, which is a plugin used to extract certain parts of your code and rebuild the import address table. Okay, now from here we're gonna have to use AAT auto search to rebuild the import address table. Result of advanced and normal search is different. Do you want to use DAT search advanced result? Now basically, if your sample is complicated or complex, you want to click on yes. But if the sample is a small sample such as this one, we can skip the advanced search for the import table. And as you can see, we have some entries, right? You will want to get these imports. I'm going to click on get imports. And as you can see, we have some valid entries and some invalid entries. These invalid entries, we can remove them. We can safely remove them. So we can right click and select on cut the chunk. All right, the next thing we want to do is to fix dump. Click on any one of these. Gonna click on this one, and as you can see now, import rebuild success. The new sample has been saved, and there is an as you can see, an extension that indicates the name of the plugin used. Okay, click on X, and we're gonna stop here. All right, so we have a new sample here. How do you know that this is the part that is unpacked of the code? We can verify this by using detected easy. If detected easy indicates that the sample is packed, we still have a problem. If it indicates that the sample is unpacked, it means we have been successful at dumping the unpacked version of the executable. So now detect it easy, and here let's have a look. So the compiler used is Microsoft C++, and here is the linker. If you click on the entropy, you can see now it is 70%, which is way lower than 97%. This is the unpacked version of the sample. Still we have packed sections such as section 0, but have a look at the other sections. They have been unpacked. You can also verify this by going to PE Studio and importing the new sample. Okay, let's have a look at these sections when they become available. Okay, now we have some sections that have been changed. Take a look at this. This is the name of the plugin, and these are the changes that have been done by the plugin. Still we have some parts that are still packed, but as you can see the entropy is way lower than in the previous sample. Now your next step is to analyze the file again with the debugger, resting assured that the sample now is unpacked. Now in the last section of this video, we're going to answer the questions in this room. Task 2, scrolling down, let's see here. What is the name of the Windows API function used in a common anti-debugging technique that detects if a debugger is running? It is debugger present. It's used along with other API calls to verify or to validate if a debugger is running. Task 3. What is the Windows API function that enumerates windows on the screen so the malware can check the window name? It is enum windows, and it is also used with other API calls to find out if a debugger or a VMware process is running. What is the hex value of NOP instruction? It is 90. What is the instruction found at memory location CB? Well, we can find this by looking at the demonstrations here in this room. So here we're looking to find the instruction found at memory location. Let's see here. So looking at this screenshot, we have this memory address at the very end and indicates this instruction, adding 8 to the stack pointer. Task 4. What is the name of the identifier process used by malware to check if the machine is running inside VirtualBox? So usually this is the process name of VirtualBox program. What is the OUI automatically assigned specifically to VMware? If you remember, we have answered this when we talked about VM detection. Using Task Manager, what process indicates that the machine for this room is an Amazon EC2? Okay, let's see. Task Manager. And here it is the process name, Amazon SSM agent. Task 5. In the C code snippet, what is the full WQL query used to get the temperature from the Win32 temperature probe class? So retrieving the temperature of the machine is one of the methods the malware uses or may use to find out if it is virtualized. Why? Because the Win32 temperature probe class, if you Google this, you will see this class represents the properties of temperature sensor. Most of the information that the Win32 temperature probe provides comes from the SM BIOS. Real-time readings for the current reading property cannot be extracted from the SM BIOS tables. So for a virtualized environment, this reading will not be supported. It's not going to be clear what is the reading. But for physical machines, it will be retrieved from the SM BIOS table and given back to the OS. So malware sometimes rely on this tactic by probing or reading the value of this class to find out if it is recognized, such as indicating real value, or not recognized, indicating that the machine may be virtualized, because not all the time this value can be retrieved from the SM BIOS tables. Some machines do not support this table. So in the C code snippet, what is the full query used to get this class? Let's see the C code here with the C code of this room. There's the C code. Let's have a look. So here is the beginning, proceeding with non-malicious activities, proceeding with malicious activities. So the malware here has two outcomes or two operation modes. It either runs with non-malicious activities or it runs with malicious activities. All depends on the call to this function, has thermal zone temp. This is the function, and here we're gonna have to see where it reads the value of this class. Okay, so here it is. Execute query WQL select from thermal zone temperature. This is the query that the malware executes in order to read the value of this class. What register holds the memory address that tells the debugger what instruction to execute next? Well, it is the EIP. It is the instruction pointer. Before uReturn is compared to 0, what is the memory location pointed by EBB-4? Okay, so here we're gonna have to maybe interact with the sample. So we go ahead, and here we're gonna examine the VM detection capabilities of a sample. So file, open, click on VM detection, and then F9, and here we have a look at the entry of this function. As you can see, if you look at the instruction pointer here on the very right, you can see the address of the memory address of the instruction that will be executed, and it is VM detection. Back to the question. Before uReturn is compared to 0, what's the memory location pointed by EBB- or -4? Before uReturn is compared to 0, let's first locate the instruction that compares uReturn to 0. If you want to have a quick access to this instruction, click on the hint, have a look at this memory address, go to here and right click, select go to expression. Let's see. Compare EBB-18 0. This is the instruction that compares the uReturn to 0. We want to find out the instruction before this. The instruction before this moves EX register to the memory address indicated by EBB-4. The question here is to find what is the location pointed by EBB-4. That's easy. Right click on this, select follow in disassembler or follow in dump. I prefer to follow in dump. Follow in dump will give you the address in this area here. It's gonna have a quick look at this. So right click, follow in dump, and select address EBB-4. Let's see here, it's highlighted in red, 7C, and this is the memory address. But you want the beginning of this, so you're gonna have to select where it starts. It starts at here, 1C. Let's see, up. So go to the hexadecimal representation, you're gonna have to select this one, 1C. This is your address. Or maybe this is the beginning of the memory location pointed by EBB-4. Packers. What is the decoded string of base64 encoded string? Well, use CyberChef. As you can see, this is the answer. Task 7. According to Detected Easy, what is the version of the Microsoft linker used for linking packed? Okay, I think we have covered this in the previous video. Let's close this one. Close the debugger, stop everything, and we're gonna have to analyze the packed malware. We did that a while ago. We're gonna have to now to extract the version. To extract the version, we're gonna have to analyze the unpacked version. Detected Easy. Click on this, and supposed to have the version here, 15.9, 14.16. What's the version of Microsoft linker used? This is the linker. Yeah, it is 14.16, right. According to PE Studio, what is the entropy of the UPX2 section of the packed executable? And I have to open this with PE Studio then. Click on the unpacked version. The entropy of the UPX2 section having the sections to come up. Okay, UPX2, the entropy is 2.100. Well, here it says 2.006. You're gonna have to find out why. Okay, let me open the sample, the original sample maybe. Okay, so UPX2, it is 2.006. Okay, that's the answer. So here you have to analyze, or you have to open the original sample, the packed one. Conclusion, and this is finished.